All right, let's jump right in. We're going to follow the flow of electricity through something that is, well, it's totally critical to our modern world, but most of us never even give it a second thought.
I mean, really think about it for a second. You flip a switch, and boom, light. It just happens. But what goes on between those massive power lines you see on the side of the road and the outlet right there in your wall? Well, there's this incredible, kind of hidden step in between. And the secret? Well, it's all right here, inside an electrical substation. This block diagram? This is going to be our roadmap for this whole explainer. It shows us the entire journey, step by step, that electricity takes from just raw, untamed power to the useful energy that we actually use. So, what is a substation, officially speaking? Well, the source material basically describes it as a place where electricity gets a complete makeover. It's where its characteristics, and the big one is its voltage, get changed to make it safe and, actually useful for us. Okay, so let's get to our first big stop on this journey. This is really the heart of the whole operation.
If you look back at our map here, you'll see the power flows straight into this big central block, the transformer. And yeah, the manual calls this the main device of the substation. And trust me, it's for a very, very good reason.
So its job is, on the one hand, simple, but it's also absolutely critical. Think of it like a voltage translator. It takes this incredibly high, super dangerous voltage coming off the main grid, and it steps it down to a level that, won't literally fry every single appliance in your house. And the scale of this change? It's just staggering. We are talking about taking 11,000 volts of raw power and taming it all the way down to 440 volts. That is a huge, massive reduction. And frankly, it's the key step that makes our entire modern electrical world possible.
And if we could kind of peek under the hood of one of these things, we'd find the key parts. A big magnetic core and a bunch of copper windings. That's what does all the heavy lifting. Then there's transformer oil to keep everything cool while it's working hard, and this really clever safety gadget called a Buchholz relay that's basically standing guard to protect the whole unit.
Okay, so we've stepped down the power. It's safe for now. But how do we control it? How do we switch it on and off and protect everything? Well, this is where the system's gatekeepers and bodyguards come into play.
Let's head back to our map for a sec. You see these blocks on either side of the transformer? That's the switchgear. You've got one for the high tension side, that's the high voltage coming in, and another for the low tension side, the lower voltage going out. These things are literally the first and last line of defense.
So this switchgear stuff has two really important jobs. The first one is just routine control, switching things on and off. But its most important role, that's protection. It's designed to automatically cut the power if something goes wrong, like a short circuit or an overload, and that prevents just catastrophic damage.
Here's a good way to think about it. The high-tension switchgear is like the bouncer at a big concert. Its main job is to protect the star of the show, the transformer. Then, the low-tension switchgear is more like the friendly usher, safely guiding and managing the now much calmer, lower voltage power as it heads out to all of us.
All right, now we're getting to what I think is the coolest, most fascinating part of this entire system. We've made the power safe. Sure, we can control it. But how do we make it efficient? This is where a little bit of, it's kind of like electrical engineering magic happens. Okay, so first things first, we got to understand that not all our gadgets use power in the exact same way. The source material breaks it down into three types. You've got your simple resistive loads, think old-school incandescent light bulbs. But the really key category for us, for the modern world, is this third one, inductive loads. And that's basically anything with a motor in it. Fans, refrigerators, washing machines, all that stuff. And here's the problem. Almost everything we use today is inductive. And all those inductive loads create this thing called a lagging power factor. Now, in simple terms, that just means the electricity isn't being used as efficiently as it possibly could be. The swing analogy is perfect. It's like you're trying to push a swing, but your timing is off. You're still putting in the effort, but you're just wasting a ton of that energy. And this inefficiency, it has real-world consequences, like it costs money. It creates more copper loss, which is just a fancy way of saying wasted energy that just turns into heat. It means you need bigger, more expensive equipment to get the same job done, and you even need thicker, more expensive copper wires to carry that extra current. It's wasteful from top to bottom. So let's make this super concrete. The manual gives a great example. Let's say you've got something that needs 800 watts of power to run, okay? Now, if your system is inefficient, let's say it has a power factor of 0.8,
You actually have to pull 1.3 amps of current to get that 800 watts of work done.
Okay, but now watch this. If you improve the efficiency, get that power factor up to 0.95, which is way closer to perfect, the current you need drops to just 1.1 amps. You are getting the exact same amount of work done, but you're using way less current to do it. That is the power of efficiency right there.
So the big question is, how do they do that? How do they fix it? Well, they use this really clever piece of gear, the Power Factor Improvement Plant, or PFI plant. It's basically a big bank of capacitors that fights back against that lagging effect from all the motors, and it pushes the whole system's power factor right back up toward peak efficiency. It's kind of like the system's own personal efficiency coach.
Okay, so let's recap. Our electricity is now safe, it's controlled, and it's super efficient. We are on the final leg of our journey here. It's finally time to send this power out into the world.
So, back to our map one last time. You can see the path now. The fully processed power is flowing from that low-tension switchgear and heading out to the DBs. That stands for distribution boards.
And a distribution board is, well, it's pretty much exactly what it sounds like. It's the final hub. It takes this big bulk supply of ready-to-use power and it just splits it up, sending it out through all the different circuits to every individual thing that needs it. The lights above your head, the outlets in your wall, all the machines on a factory floor.
And that's the journey. Pretty amazing, right? We followed the flow from this wild, untamed, high-voltage river of power, watched it get tamed by transformers, controlled by switchgear, and optimized by efficiency plants, until it finally becomes the safe, reliable electricity that we depend on every single second of the day.
This entire, incredibly complex system just hums away in the background, totally invisible, powering our entire world. It really makes you wonder, doesn't it? What other pieces of critical infrastructure just like this are out there? Things we rely on every single day, but just never give a second thought to.